Recording has started. Hi everyone, welcome to Machine Learning with Python. We are on the session 5. This is classification problem. We call it previous one we had uh, done that was also related to supervised learning. So supervised learning 4.1 and 4.2 uh, generally focused on the regression, which is number based, and here classification is label based, which is text based. Jamie Tosawa has been doing this machine learning with Python uh, and entire course work which is related to PG diploma in artificial intelligence preparation for the course work, etc. Whether you do a JEE or whether you do, it is a postgraduate, so any graduate is welcome to, or any career oriented person who wants to pursue can at least learn from this. You don't have to really um, attend everything. You can also attend and read the recorded ones. And so we are very much happy to see that a lot of people have learned and used this, and we welcome that you can use this. With that, I will hand over to Jamie Tosawa, our experts in machine learning, and he's doing machine learning this time with Python for the classification problem 5.1. Go ahead, take over, Jamie.
So thanks for the introduction, sir. And so welcome everyone for the machine learning with Python. And today's session will be conducted on classification problems. This is the first iteration of the fifth session. So let's get moving and let's get started with the classification problems. So first, what will be our goals in this session 5 or session 5.1 to be precise? We'll be understanding the concept of classification problems and the applications across the different sectors, then learn to build a logistic regression model and decision tree models using the Python's package, stats models, and scikit-learn APIs. Then learn to perform the activities which are splitting the data set for training and testing purposes, then building the Python package on training dataset and test on the validation dataset. Building model using the Python package. Then learn to measure the model accuracies using offline metrics, using the confusion matrix, then sensitivity, specificity, precision. These are some of the metrics used for evaluating the model's performance in an offline manner. Then receiver operating characteristics curve and the area under the ROC curve or AUC, area under the curve. Then learn about the statistical significance, model diagnostics, and find the optimal cutoff probabilities for classification. So these are the objectives for today's session. So let's get started. So I'll start with a step back rather than directly moving into the session. So what is artificial intelligence? It's a broad field, and in general, or in very common terms, we can say that it's an ability for the computer to think and act like human, and we can collectively say it as AI. And in the diagram below, you can see the Venn diagram below. You can see the relationship of artificial intelligence, the machine learning ML, and the DL, which is deep learning. So deep learning being the subset of ML, ML being subset of AI. Deep learning gives us a really deep insight into the things and performs some really complex tasks for us. Then comes the machine learning. Machine learning is when we train a model on a given data set and the model learns to perform the task and tries to match the output that we want and make desired adjustments into the model to get the desired output. Moving forward, these are some of the ML categories. We have supervised learning, unsupervised learning, and reinforced learning. I'll start with unsupervised learning first. The unsupervised learning means that you let the machine learning model make sense to the data, or try make the model know what kind of patterns uh, can be there in the underlying form in the data set. So its subcategories are clustering, association, and dimension reduction. Clustering is nothing but clustering same kind of data points in a 2D space, for example, and then all the clusters or all the groups of data points which are close together can be formed into can come under a single cluster and help us recognize which cluster that particular cluster belongs to. Then next is association. Association is nothing but creating an association with two items, or not necessarily two items, but for example, let's say two items. So if we are getting a hair care product, so if we are buying shampoo, then the association can be made with hair oil. If we are trying to buy a breakfast, so with purchase of a bread, you can be recommended by the model to buy milk or eggs, etc. Then dimension reduction. Dimension reduction is nothing but a technique to uh, remove the features from the data set while keeping the originality of the data set as much as possible. Then comes the reinforced learning. Reinforced learning is nothing but a trial and error kind of method where the machine keeps on learning by continuously trying to perform a task and handling the error, and also keep on learning the task and improving with each iteration. So one of the examples, or one of the common examples, being a robot trying to learn the shape of a room by continuously colliding and learning the path of the room, not colliding, and calculating its area. Then comes the supervised learning. Supervised learning is nothing but we know the output of the task beforehand, and we are trying to make the model learn to get to that output or get to that efficiency or accuracy by continuously training the model and adjusting the model according to the need to get to the output. So regression and classification are two of its subcategories. Regression is nothing but working with the continuous values, prediction of house prices, prediction of height in some region, etc., are comes under regression. Then comes the classification. Classification is nothing but a certain kind of uh, data points belonging to some classes. It can you can say a model predicting a picture of a cat. If it's a if it's a binary, then a model predicting a picture of a cat, or it is not a cat. So there are two classes, means binary. So a model is trying to predict the picture of a cat, or the picture is not of a cat. But if it's a multi-class, it will try to predict which animal does the picture belongs to, whether it's a horse, a dog, a cat, etc. So that is what the multi-class classification means. In this session, we'll be discussing the binary logistic regression. So let's get started with a binary logistic regression. Some of the examples of classification first are a bank trying to classify the customers based on low and high risk. Then second example being the e-commerce providers trying to predict whether a customer is likely to churn or not churn, as it depends on as those things uh, depends on the affect the revenue of the company, especially when the customer has been for a long time or is a highly valued customer. Then the health service provider may classify a patient based on the diagnostic results as positive or negative, positive being presence of the disease and negative means not. Then HR department of a firm may want to predict if an applicant would accept an offer or not. Then the predicting outcome of a sporting event, for example, whether the sports team will win the next World Cup or not, or win a particular tournament. Then sentiments of a customer on a product or service may be classified as positive, negative, neutral, and sarcastic. Then based on the image of a plant, trying to predict if a plant has a disease or not, or has a specific kind of disease or not. So some of the techniques that are used for the classification are logistic regression, classification trees, discriminant analysis, neural networks, support vector machines. Logistic regression is something the topic of today. Classification trees are trees being used to make certain kind of decisions based on the conditions being the uh, dividing factors or the classificating factors of the trees. Then discriminant analysis. It's a statistical technique used to classify observations into groups based on their characteristics. It seeks to identify the linear combinations of variables that best discriminate between two or more groups. Then neural networks are nothing but trying to enact the way our brain works, having some neurons, and those neurons uh, organized in a layer, and each layer acts on different terms or a different function and tries to achieve a task in a human brain like manner. Then the support vector machines, it's trying to classify by separating the data points with the use of a hyperplane and finding the most optimum uh, feature space while maximizing the margin between them. So what is logistic regression? A supervised machine learning algorithm that accomplishes binary classification tasks by predicting the probability of an outcome, event, or observation. The model delivers a binary or dichotomous outcome limited to two possible outcomes: yes, no, 0, 1, or true, false. The last statement holds true for the binary logistic regression. So binary logistic regression. First of all, the logistic regression is kind of it's actually a misnomer, and it's not used for regression, but rather used for classification. The logistic term comes from the word logit or log odds, and we'll see further when we discuss the mathematical representation of it. So there will for probability of an observation y belonging to a class. If y's value is equals to 1, it belongs to a class, and if y's value is equals to 0, it does not belongs to a class. So for a probability of y equals to 1, the mathematical expression can be written as e raised to z divided by 1 plus e raised to z, where z is nothing but beta 0, the intercept, plus beta 1 x1, beta 1 being the coefficient, plus beta 2 x2 till beta m xn, where x is nothing but the input features. So if the logistic regression is plotted on the graph looks something like an S-shaped curve, which is also known as sigmoid function. And you can see the in the image what the graph would look like. Now, the log odds that I mentioned before, this is what the expression would look like mathematically. So log of a probability of a class belonging to an observation belonging to a class, which is y equals to 1, as discussed earlier, divided by 1 minus the probability of belonging to a class, or a probability of y equals to 1. Or this can also be said as a probability of belonging to a class divided by probability of not belonging to a class. So log of p, probability of y equals to 1 by 1 minus probability of y equals to 1 equals to z, where z is nothing but beta 0 plus beta 1 x1 till beta m xm. So the left hand side of the above equation is a log natural of odds and is known as logit function. The right hand side is a linear function. They are called generalized linear models, or GLM, and in GLM, the errors may not follow normal distribution, and there exists a transformation function of the outcome variable that takes a linear functional form. So for example, if a person is having a heart disease or not based on their age, the mathematical expression can be written as, or mathematically it can be represented as probability of heart disease equals to 1 equals to e raised to beta 0 plus beta 1 age divided by 1 plus e raised to beta 0 plus beta 1 age. And for that, you can also see the S-shaped curve depending on the age and the probability. And also the age here being the independent variable. So today's session, we'll be taking the example of a journal credit rating, and we'll be using the dataset for the same. And you can see the description of various categories that the dataset uses in order to categorize various categories uh, uh, that are used in the dataset. So for checking, you can see the alien A11 to A14 are the categories. For A11, which is less than 0 DM, to A14, which is a no checking account. Then the duration, it does not have a specific category to it. Then a credit history. So A30 to A34.
So this is Deutschmark, right?
Sorry?
Deutschmark. Deutschmark. DM is Deutschmark.
Yes.
German currency. Okay.
Yeah. So A30 to A34, A30 being no credits taken or all credits paid back duly. Then all credits at this bank paid back duly. to the A34, which is a critical account, others account or other credits existing not at this bank, and uh, and for all the categories, let's say for saving accounts, if we have A61 to A65, less than 100 Deutschmark, to A64, which is greater than or equal to 1000 Deutschmark, then A65 for unknown or no savings account. Then for the employability of the person, for A71 to A75, A71 being unemployed to A75 greater than equal to 7 years. Then interest rate, there is no categorical one for interest rate, but for personal status, for married, divorced, separated, single, each one of them for male and female, and divided into A91 to A95. Then again, residing sense and age are not the categorical ones that have been created, but then the interest plans, the installment plans of the applicant. So if A141 for bank to stores, and A143 for none. Then the balance in the checking accounts, this is the same that was discussed before for A11 to A14. Then the job status, on A171 unemployed, unskilled, non-resident. Then 172 for unskilled but resident. Then 173 for a skilled employee or official. Then management and self-employed, or highly qualified employed or officer. And in the end, the status, which is good credit for 0 and bad credit for 1. Remember the thing that bad credit is for 1 for this. So if we get the information of the data set, this is what the information, this is how we'll get the information. First of all, we'll import warnings and filter the ignored warnings. Then the importing pandas as PD and NumPy as NP. Then we are creating a data frame, the credit DF, and reading the data set. And then when we get the info of the credit DF, this is the information that we get. So we get the number of columns, number of entries that are present, then all the columns starting from 0 to 13, which makes it 14 columns in total. Then the data types, which are int and object. So all the categorical ones are called the object data types, or the categorical data types will be recognized as object data types, and the memory used for using the data set. So these are all the columns of the data set, and we are printing the top 5 entries of it. So remember the account categories, which are A11 to A14, and based on the balance, those categories were done. So this is what the A11 and A14 A14 means. So to find the values of the good and the bad credit, we can use the data frame, which is the credit DF over here, the status, and the value counts on it. So we are getting 0 for 700 entries, and 300 for 1. Means 700 entries on 0 and 300 entries on 1. So we have 700 good credit and 300 bad credit. Remember, the bad credit is 1 over here. There are 700 good credits and 300 bad credits, as mentioned before, also for the 1,000 entries in total. If we want to create a classification model, uh, we'll first create the X features. So, so we'll be creating the X features, uh, which will be used for the list. We'll be first listing all the features in column for the credit DF and getting all the columns, and then the status column that we are trying to predict the outcome of will be removed, because that's what we are trying to predict. And then we'll print the X features. So for all the columns that we had, you can see the status column has been removed. The status column was on the last, which should come after the job over here, but as we have removed it, so it won't. Then there are categorical features. Those features have to be uh, one hot encoded. So for those categorical features, we have to make dummy variables, and we'll be taking n-1 dummy variables to avoid the multi-collinearity, or also known as a dummy variable trap. And we'll see in a moment why we say that. So multi-collinearity is when the variables are very linearly dependent on each other. So it means that the sum of all the dummy variables equals 1 for any given observation. This leads to perfect multi-collinearity, where one dummy variable can be exactly predicted from the other. Then the linear dependence. Let's say if there are three colors, and if there are not the first two colors, then it's the last one. And that is what the linear dependence means in the dummy variable trap. And let's see in detail what the statements have to say. So including all the n dummy variables introduces a redundancy, because one category can be expressed as a combination of others. For example, if you have a categorical variable with three categories A, B, C, you only need two dummy variables to represent them. So dummy one if A, zero otherwise, and for dummy two, one if B, zero otherwise, and the third category C can be inferred. If dummy one and dummy two are both zero, then the category C, and then it has to be category C. And to avoid that, we use n-1 variables. So by dropping the category C, we have no way to infer that it can be C, and therefore we can make or actually predict by avoiding the dummy variable trap. The encoding categorical features will be using the pandas get dummies function to encode the categorical features. So for the encoded credit DF will be used on so the first the PD get dummies will be used on the features that we have created, and then it will be stored into the encoded credit DF. So if we print the encoded credit DF in a form of list, these are the outputs that we will be getting. And as we have uh, uh, dropped the, you can see that one of the parameter is drop first equals to true. Here the checking account A11 has been dropped in order to avoid the trap. Now, checking account variable is encoded into following three dummy variables and the base category. So the checking checking account A11 is dropped as just seen. If all the following three variables values are set to 0, it indicates that the account type is checking account A11. You can see when we tried to print the first 5 values of the dummy variables that we have created. The first value itself can be inferred as if it's none of them, then it's A11. Then next, we start by splitting the data set. For that, we'll be using the stats models API and the logic function for the logistic regression, and using both of them to create a logistic regression model. So remember the mathematical, just a second, the mathematical expression over here, the beta 0 being the intercept. So we'll add a new column and set its value to 1 for that, and for the model to estimate the intercept. So the darkened text is nothing but the code of Python. So we will be importing the stats model.api and using SM as an alias, then y being the credit df, then stat models add constant for the intercept. Then using the scikit-learn sklearn.model selection and importing the train test split. So train test split is nothing but the splitting of the data set. So the training data set over here, you can see the train test split. In the parameters, the test size is 0.3. So we are doing a 70-30 ratio for a train and test respectively, and the random state being equal to 42. Then starting with the building the logistic regression model, the importing the stats model API as SM, then logit equals to sm.logit, and then passing the y train and x train for it, and the logit model fitting or passing the fit function on the logic for our logit model. So the fit function on logit estimates the parameters and returns the model details in the variable logit model, which contains the model parameters, accuracy measures, and residual values, among other details. So on the right side of it, of the Python code, you can see the optimization terminated successfully, current function value of 0.488, and iterations were 6. This is the report that you get on passing the logit function with fit. So if you print out the model that we created, and if you print out the summary of it, this is what the summary you get for it. This is what the summary looks like. So for diagnose for a model diagnostic or trying to evaluate the model, or which are the factors which can be used to improve the model, we'll be using the Waltz test, likelihood ratio test, then pseudo R square. So Waltz test is used to test the significance of individual predictors. Then likelihood ratio is used to compare the fit of nested models, determining if additional predictors improve the model. And R square provides an indication to the model's overall goodness of fit, which is analogous to the R square in the linear regression that we use, but adapted for the logistic regression and other models where the traditional R square is not applicable. So wherever the R square is cannot be used, pseudo R squares can be used for running the diagnostics. So according to the Walls test, for the p-value, we are getting 8 total features, which are really significant. And you can see the underline, the red underline for the probability value of those features. But this is a very manual way. If you try to do it, do it by manually checking all the rows and all the values of the p-value. So for that, we will be creating a get significant variable function. So where the values of point which are less than the values of 0.05 for the p-values in the data frame. You can see over here the p-values of the data frame. Those will be returned. So the get significant variable is returning a list of the p-values which are smaller than 0.05. So, so when you run this code and run the significant variables on our logic model that we just created, the output would be these 8 columns, which were duration, amount, interest rate, age, checking account A13, then checking out A14, and credit history A34, and saving accounts A65. So these are the some of the significant or these are the most significant columns according to the Waltz test. So now we'll be using those columns, those most significant columns, and then making another model. So using the stats model dot logic or sm dot logic, and then for the y train and for the add constant x train on the significant variables, and then fitting on it. So or passing the fit function on that. So the output we get for this is 0.051 as the current function value, and number of iterations was 6. And when we finally print the summary of the final logic, which is the new model that we have created, this is the summary that we get. So for the summary that we have got, you can see the negative sign in a coefficient value indicates that as the value of this variable increases, the probability of being a bad credit decreases. That which means that py of 1, py equals to 1 decreases. Probability of y equals to 1 decreases. Then a positive sign means that the probability of being a bad credit increases as the corresponding value of the variable increases. And some of the other observations for the model summary: the log of odds ratio or probability of being a bad credit increases as duration, amount, interest rate increases. And so 1 unit change in the duration results in 0.019 unit change in log of odds ratio. The probability of being a bad credit decreases as age increases. This means that older people tend to pay back their credits on time compared to the younger people. So now predicting that on the test data, we have been using the training data. So now we'll be using the test data and using the final model on the test data. So we'll be also using the significant variables that we created using the Waltz test with predict, and using a new data frame to compare for the accuracy measures. So YPredDF is used in order to make the data frame, and Y-test for actual, and the predicted probability for the final logic predict, which are taking the significant variables from the X test that we have taken and passing it on with the add constant on the stats models. Then using the sample function to print few of the uh, observations with a random state of 42. So here we have used a sample function on the YPredDF that we have created, and we have chose to print 10 observations with the random state 42. Now checking the observations classified correctly or wrongly by the model. So here we are going to assume that the cutoff probability for the prediction that the model has made, the cutoff probability is 0.5, not 0.05, but 0.5. So if the probability values are greater than 0.5, those are bad credits, and rest of them are good credits. And also remember, we are using bad credit, or we are representing bad credit with 1 and good credit with 0. So we'll be using the map function of Python in order to map the probability of 1 and 0. So the YPredDF that we created, that will be used and will be mapped with if x is for all the values of x which are greater than 0.5 will be marked as 1 and as 0. And again, printing the values using the sample and printing 10 values. So you can see the image on the right, and starting with the observation 557, the predicted probability is 0.08. The actual probability is 1, which is actually a bad credit, but it has predicted as 0. Then coming to the observation 332, which is actually a bad credit, the probability that has been predicted by the model is 0.83, which is a good probability, and the prediction is also 1 for it. So in a way, the model is showing some right and some wrong results. So we'll try to improve the accuracy of it. So remember that the first observation over here, which is 557, which was actually a bad credit, but falsely showed as a good credit, which means it was a false positive. So this is what the false positive term would mean, or this is what we call a confusion matrix. So so the true positives and the true negatives are the actual values, or the true values that has been true and given as true, or false and given as false. But false negatives and the false positives are the values that for false positive, which should have been positive but given as negative, then false positive, which should have been negative but given as a positive. So this whole matrix we'll be trying to create with the help of the matplot labs pyplot and the seaborn libraries. So the darkened text on the left is actually the Python code. So we import the matplot, the cpon as their alias as plt and sm, which are really common ways to import these libraries. Then from scikit-learn, we import the matrix. Then we are trying to make a function which is called draw the confusion matrix. So the function's name is draw cm, which will take two parameters, which are actual and the predicted. Then in the confusion matrix, will the actual, predicted, and the labels 1 and 0 will be given. Then using the heat map of the cpon and using the heat map, and it's passing the parameters for it, the cm being 1, the annotation equals to true. Then fmt is nothing but the decimal value for the format. Then then x tick labels and y tick labels are nothing but the bad credit, good credit. You can see on the x-axis on the image that has been shown, and the y tick labels of bad credit and good credit. Then the overall y and x label for the true label and the predicted label, the plt.show, in order to ensure that it shows the heat map that we have created. And then we finally pass the draw cm function for pass the values of ypredf of actual and the predicted values on the draw cm function. We'll be getting this graph, or this heat map. So for this heat map, you can see that on the bad credit, on the true label, there are 30 plus 61, total 91 observations, and 30 have been truly predicted as or has been correctly predicted as a negative outputs. So this is what the interpretation of the true positive, correctly predicted positive observations, the false negatives, which are the type 2 errors, incorrectly predicted the negative observations. Then true negatives correctly predicted the negative observations, and false positives for incorrectly predicting the positive observations. The true positive and the bad credit for the image over here and over here didn't match, because we are actually trying to predict the bad credit rather than the good credit. So that is the reason the explanation and the explanation over here, if just listen out of context, it won't make sense. Then measuring the accuracies. So whenever the model is prepared, the model is evaluated first with offline matrix, or some of the matrix which are tested or evaluated before it has been used in a live format. So for models evaluation on the measurement of its accuracy in offline mode or on offline manner, we'll be testing it on sensitivity, which is also called as recall or true positive rate, then specificity, which is true negative rate, the precision, and the F score. So let's get started with sensitivity for the measuring the accuracy of the model. So sensitivity or recall or true positive rate, mathematically it can be represented as a true positive divided by true positive plus false negatives. So it takes into consideration all the positive values. So given the conditional probability that actual and the predicted values are positive for the sensitivity, then for specificity or the true negative rate gives the conditional probability that the actual and the predicted values are negative, and mathematically representing it the specificity, the true negative is divided by the true negative plus false positives. So it takes into consideration all the negative values of the data set. Then precision gives the conditional probability that actual and the predicted value are positive, mathematically representing the TP, which is true positive divided by true positive plus false positive, which measures the precision. Then comes the F score, which combines the precision and recall, the harmonic mean between the precision and recall, and mathematically F score is represented as a 2 into recall into precision divided by recall plus precision. So for our model, we'll be using the classification report method, which is in the scikit learn.matrix, which we have already imported for precision, then recall, and then for F score for each class. So if we use that for our Y prediction DF for actual and the predicted values, this is the report that we get for the by passing those into the classification report. So the precision for the good credits, which is 0 over here, is 0.76, and bad credits is 0.59. Then the recall for a point for good and bad is a 0.9 and 0.3, and F1 score for good and bad is 0.8 and 0.42. So precision for a bad credit, which is class 1, indicates how many of the predicted bad credit instances were actually bad credit. Then recall for bad credit indicates how many of the actual bad credit instances were correctly predicted. And the F1 score for bad credit balances the precision and recall, providing a single metric to evaluate the performance on predicting bad credit. So F1 score, which is 0.42, can still be improved. So the model is not good at predicting the bad credit, and it is due to the cutoff, which we have used as a 0.5. Remember, 0.5 was used in order to bifurcate the good and the bad credit. So we can improve the performance by choosing the right cutoff. So we can use the distribution to see how well the model can distinguish the bad credits from the good credits. So for that, we'll use this histogram. And if we plot, so starting with the Python code, so image is pretty easy to understand. So starting with the Python code, which is the starting text on this slide. We'll be using the seaborn disk plot, then plotting the actual values in the ypred df that we have created. Then passing the color, the label as bad credit. The KD of the parameter that is equals to false over here is nothing but an estimate of line that will go through if we pass it as true. So first we have used the disk plot for predicting the predictions of the actual values. First we have created the disk plot for the bad credits. Now we'll be creating the disk plot for the good credits on the same. on the same disk plot, and then the make sure the legend, which is the markings on which marking belongs to which is showed, and to show the plot in the end. So this is the plot that we get when we run the code. So larger the overlap between the predicted probabilities for different classes, higher will be the misclassifications. So now we'll be starting with the receiver operating characteristics, or ROC, and the area under the curve, which is AUC. So ROC, or receiver operating characteristics, is a graphical representation that illustrates the performance of the binary classification model across various thresholds. It plots the true positive rate against the false positive rate at different threshold settings. The ROC curve is a plot between the sensitivity on the vertical axis and 1 minus specificity, false positive rate, on the horizontal axis, x-axis. And the area under the curve, the area under the ROC curve quantifies the overall performance of the model, under where higher higher AUC indicates better discrimination ability between the positive and the negative classes. So in absence, ROC and AUC provide insights into how well a classifier can distinguish between different classes, making them essential tools for evaluating and comparing classification models. So when working with ROC and AOC, how we'll work with it is, first we'll be creating a function called draw a ROC. Then using the matrix.roc curve, which will return the different threshold or the cutoff values for the corresponding FPR, or the false positive rate, on x-axis, and the TPR, which is true positive rate, on the y-axis. Using these values to create the ROC, the matrix ROC and AOC score function will be used in order to return the area under the curve, or AOC. So the matrix returned by the matrix.roc curve will be used in order to calculate the area under the curve. It will be a single process, not something that we have to calculate in a separate manner. So you can see the diagram on the bottom left, a diagonal line separating the figure, or the graph, and the readings. So let's see what the diagonal line means, and what is the interpretation of being above or below the diagonal line. So the area below the diagonal line is equal to 0.5, which is our cutoff, and that we have decided, if you remember. So this creates a perfect right angle triangle, and the area which will be equals to 0.5 AB. And here the values of A and B are equals to 1 for our case. So sensitivity or specificity are likely to change when the cutoff probability is changed. So whenever we will change the cutoff probability for our improvement in the model's prediction values, the sensitivity and the specificity will change. So the line above the diagonal line in figure captures how sensitivity and 1 minus specificity change when the cutoff probability is changed. the model with higher AUC is preferred, and AUC is frequently used for model selection. So AUC of 0.7 is required for practical applications. AUC of greater than 0.9 implies an outstanding model, and caution should be exercised while selecting the models based on AUC, especially when the data is imbalanced. Imbalanced data set is, let's say there are more positives than negatives, or more negatives than positives. So AUC can be very high under those imbalanced data sets, but the sensitivity or sensitivity or specificity values may be poor. So for the graph that we have created, you can see the area of curve and the area, which is 0.78. So if you want to separately get the ROC AOC curve, you can use the matrix dot ROC AOC score and passing the values on it for the AOC score. So finding the optimal classification cutoff. Remember, we have discussed the cutoff over here. The diagonal line represents the cutoff, which is 0.5 over here. And for the cutoff of 0.5, we are not getting the desired efficiency or accuracy from the model. So we are trying to calculate now what will be the efficient cutoff probability for our model, which will improve the model. So choosing the right classification cutoff probability, the accuracy, sensitivity, and specificity will depend on the chosen cutoff probability. So these are the metrics that we have discussed before, and these matrices value will be affected whenever we choose the cutoff probability. So two methods we will use for selecting the cutoff probability, which is Uden's index and the cost-based approach. So let's start with the Uden's index first. So Uden's index, which is also known as J statistic, takes the maximum values of the sensitivity of P plus specificity of P minus 1. Or the Uden's index can also be represented as a true positive rate plus true negative rate minus 1. The variable threshold captures the corresponding cutoff probabilities, and we can take the difference of TPR, true positive rate, for FPR, false positive rate, and then sort the values in descending order. So for the data frame that we have created, creating the FPR, TPR, FPR, and creating a data frame for them, passing the thresholds as thresholds, TPR as TPR, FPR as FPR, from just a second. So the TPR and FPR used over here has been taken from a previous code that we have used for creating. So that same TPR will be used, and then the difference will be calculated for it, and then those values will be sorted. Those TPR and FPR values will be sorted in ascending order, or sorry, in descending order, in order to get the most optimum threshold. So if we pass these values, or if we run this code, we'll get the threshold values for and the FPR, TPR values and the differences. So the optimum threshold value that we get is 0.22. You can see for the observation 160, the optimum threshold value we are getting is 0.22. So now remember the Y prediction DF that we have created and we have been using it. Though that Y prediction DF will be used on the cutoff of 0.22 rather than 0.5 that we have been using till now to predict the bad credit. And when we pass the same uh, for the value of cutoff of 0.22 and then draw the confusion matrix again for the Y prediction DF of actual and the predicted values of the uh, new predicted values. You can see the heat map or the confusion matrix that we created using the heat map has changed, and the bad credit is predicted very well now. Bad credit and the good credit has been predicted in a better manner, or there is an improvement in the model. So the report will be printed with the cutoff probability of 0.22. So the classification report that we have already seen before for the precision, recall, and F1 score. If you remember, if we print the same classification report, you can see the F1 score has been improved for 0.72 of class 0 and 0.61 for class 1, which is a bad credit. So as I said that the model has improved on the F1 score and is predicting the bad credits better. For this is just a comparison of the values before and after. The values of the report on the left is the older report, and the values on the right are the newer reports. So you can see the difference in the F1 score on the bad credit, the from 0.42 to 0.61. Now, the other optimization classification cutoff, or finding the most optimal cutoff, the second approach was cost-based approach. So as the cost of the false negatives and the false positives is not same, the optimal classification cutoff probability can be determined using the cost-based approach, which finds a cutoff where the total cost is minimum. So in the cost-based approach, we assign penalty cost for miscalculation of positives and negatives, and find the total cost for a cutoff probability. So the optimal cutoff probability is the one which minimizes the total penalty cost. Assuming that the cost of the false positive is C1 and that of the false negative is C2, the total cost will be false negative into C1 plus false positive into C2. So for a cost-based approach, we'll create a function called get total cost, where the parameters will take the parameters for the function will be actual and the predicted values and the number of false positives and the false negatives, and return the total cost of it. So this is the description of the function that we'll be making. The Python code is below, which is for the get total cost, the actual predicted values, and the number of false positives and the false negatives as the other two parameters. Then using the CM matrix for NP array and passing CM into it, and then returning the formula that we have discussed before as a result for the parameters value, and then creating a data frame for storing the information and that we got. So for in our case, we are going to assume that the false negatives which are the predicting a bad credit to be a good credit are 5 times costlier than false positives, which are predicting a good credit to be a bad credit. So deciding the cost will require domain knowledge. So uh, we can calculate the penalty cost for each cutoff probability values between 0.1 and 0.5 with incremental values of 0.1 and store the cost in ascending order to find the cutoff probability at which the penalty is at the minimum. So using a for loop where a probability for range 0.1 to 5, we are and using the get total cost function that we have created before, this one, and passing the values of the prediction y predicted values of the data frame and the predicted probabilities, and mapping those probabilities using the Python's function. And then in the end, sorting those function with the sort values cost ascending equals to true. And when we print those values, the image on the right can be seen, the probability and the cost of it for the 5 observations that we have printed. So the lowest cost is achieved at cutoff probability 0.14 if false negatives are assumed to be 5 times costlier than the false positives. False negatives are assumed to be 5 times costlier than the false positives. So for the so as we have for Waltz test, sorry, the Udens index, we have used the probability 0.22 as our cutoff probability. We'll be doing the same for the Y prediction DF and passing it for the prediction of 0.14 because we got the 0.14 as the probability. So for this probability, you can see the improvement in the function, improvement in the model's performance for the prediction of the bad credit, which went to 85. So before we end this session, let me show you the notebook for which we have created this whole session. So as you remember, so this notebook will also serve as a summary of the whole session that we have conducted. So we started with the importing the useful libraries for our use case, and then reading the data set. So remember that we use the German credit data, and we read the data set, and we printed the information regarding it. And this is the information that we got for all the columns that are present and all the number of entries that are present. These are all the columns that are present over here in the data set used using the credit df ilog. 0.5 is nothing but the printing the rows, and 0 to everything means number of all the columns will be printed. Then to find the values of the good and the bad credits that are present in the data set, and remember we are using the credit df as the name for the reading of the data set. So these are the class that it belongs to 0, or the good credits are 700, bad credits are 300. So for making the classification model, remember we made X features from the credit DF, and we removed the status, because status was the status over here. Status column was the one that we were trying to predict. So we took all the columns and removed the status column, and then we started building our the base of our model. So we removed the status column from here, and you can see that status column is missing from here. Then we encoded every categorical features, or one hot encoded every categorical features with get dummies, and we discussed why we use n-1 features for using the get dummies in order to avoid the dummy variable trap. Then for all the encoded credit DF, we made the credit DF, and then we used the dummy variables on it and printed the dummy variables, and these are the columns that were created. And when we so these are the are the top 5 observations for the encoded columns on checking account 1, 2, 1, 3, and 1, 4, A1, 2, 1, 3, and 1, 4. So this is what the first 5 observations look like. So now, as we have one hot encoded those categorical features, we'll be using the logic function from the stats model in order to start build spread the data set and start building our models and stuff. So using the for X, we'll be using the encoded credit DF, and Y is the prediction value status from the credit DF, that what we are going to predict. So first we'll be splitting the data set, and for keeping the data set in a particular number of observations, or keeping the data set in a fixed form, we are using the random state 42 over here. Then fitting the model using the logic function. So from the stats model SM, we are using this logic function, and we use the logic function on and pass a fit function on it. We are getting this some summary kind of summary or report. So printing the model summary on the model that we have got. This is the summary that we have that we get. I'll try to fit it into one whole screen. I think the summary is way bigger for that. So wait. So for printing the summary of the model that we have created, this is the summary that we get. Now, there are too many features, and we want to see which are the most significant features. So for that, we will be using the Walsh test and the likelihood test, which shows the statistical significant features. So building the models only using the significant features. So we use the significant variables, and then we recognize those variables and print those variables in the significant features by passing the logic model over here. So these are the most significant variables that we get, and then building a model on those on these variables. See over here, which is the final logic model that will be created. Again, passing a fit function will give us this these values for the current function value and the iteration. number of iterations. Then final logic summary, or the summary of the new model that we have created, which is the final logic, and making a summary of it. This is the whole summary that we get. Then we create the Y prediction DF for the, till now we have been using the training data set. Now we'll be using the test data set on both, and using the test data on the significant, using the significant variables on the X-test data set as well. Using the sample function to create 10 randomly used 10 random observations for our random state 42, and this is the output that we get. These are the some random samples that are used. Now, till now we have used we have used the cutoff probability of 0.5. So all the values that are greater than 0.5 are bad credits, and all the values that and rest of all the values are good credits. So we'll be using this cutoff probability for now to bifurcate the bad and the good credits. The bad credits, remember, we are trying to predict the bad credits. So bad credits is class 1 or is recognized by value 1. So we'll be recognizing the bad credit with the cutoff probability 0.5 if for 1, and for good, or for the good credits 0. So for these, we'll again use the sample function and print the 10 values, and this is what we get. Remember, we use the observation 557 for the probability being very low, and probability and the observation 332 for actually being the bad credit 1, the probability being 0.8, which is very good, and actually predicting that it's a bad credit. Whereas the 557 was a bad credit predicted as a good credit with a very low probability. Then because of instances like the observation 557, which was a bad credit recognized as a good credit or predicted as a good credit, we used the confusion matrix. So for making the confusion matrix, we use the matplot, lib, pyplot, and seaborn libraries in order to make the confusion matrix. So printing the importing the needed packages. Then remember, we used the drawCM function in order to make the confusion matrix. And remember, this confusion matrix that we have created is using the cutoff value of 0.5. So we have written the function, and then using that function in order to use the Y prediction DF for actual and the predicted values. So this is the confusion matrix that we get for 30 being the bad credit that was correctly predicted, and 61 being the bad credit that was incorrectly predicted as true. So using the classification report on the actual and the predicted values, and remember the precision recall and F1 scores that we get, the F1 score over here, which is a 0.82 and 0.42 for the model. Then we used the disk plot in order to know the capacity or see the model's capacity of distinguishing the good and the bad credit of the model, or distinguishing ability of the good and the bad credit of the model. So this is the displot that we got for that. So it should have as low of the overlapping as possible. So larger overlap between predicted probabilities for different classes, higher will be the miscalculations. So for for that, we used the receiver operating characteristics and the area under the curve, which is ROC and AOC respectively, and using both of them in order to see the performance of the model. So first we wrote the draw ROC curve function, then used the matrix ROC curve in order to get the threshold, and for which the FPR on x-axis and TPR will be used on the y-axis, and then using these values that we get to get the area under the curve. So for we made the function, and then we pass the actual and the probability values as the parameters. And when we pass the TPR, FPR, and thresholds for the predicted actual and the predicted probabilities, this is the curve that was created, and we are getting the 0.78, which is over here, as the area under the curve. So if we want to separately get the value of the area under the curve, this is how we can use the metric.roc AUC score and pass the parameters in order to get the values, and we are getting the 0.78 value over here too. So all these values were used and were taken using the 0.5 cutoff probability. So we are using, which is not we are not still satisfied with the model's performance. So to improve the model's performance, we use the Uden index and the cost-based approach. So starting with the Uden index and printing the first will be printing the using the Uden index and printing the values in the descending order to get the most optimum threshold first, and then printing the only the top 5 values of it, we get the threshold of 0.22. So using this 0.22 as the threshold according to the Uden index, we'll be using that on to calculate again on the Y prediction DF, and this is the heat map being used as the confusion matrix will be created, and this is the confusion matrix we get for that. Then again we use the classification report in order to get the F1 score, and you can see the F1 score being improved, especially for the bad credit, which was 0.42 before. The next approach for cutoff probability or trying to get the more optimum cutoff probability, the second approach was the cost-based approach. So first we created the total cost get total cost function, which takes the actual predicted and the false positives and the false negatives as the parameters. And we use the probability of 0.1 to 0.5 and trying to get the optimum probability between them by minimizing the values of the probabilities that we get for the in the cost-based approach. So using the Y prediction DF again for the predicted using the cost and 0.14. 0.14 is the probability that we got. Then drawing the confusion matrix again using that 0.14 cutoff probability. This is the heat map that we get. So this also shows the improvement in the prediction of the bad credit and the prediction of the good credit as well. So yeah, these were some of the references that were used for making this session or used in this session. I hope it helps, and thanks a lot for listening. Thank you.
Hey, Jim, it's an excellent job. It's, of course, a bit longer session than we had anticipated. That's okay. It's still 1.5 hours, less than 1.5 hours, because we started 6 minutes at 6 minutes. So what I would say is, this is good, but we need to have an answer from you as where is this Jupyter notebook you will be sharing, and how will it be applicable? How will it be possible for the students to use it?
So I have so there are two ways generally people have used it. I have used it using just the visual code. Import first installing Python, then within that installing the Jupyter notebook, then using the opening the Jupyter notebook for the desired folder and using the Jupyter notebook. But if the student already knows how to use the notebook, then we can the interested or students who are showing interest in learning, we can share the notebook that we have used for this session for them to experiment or to know how they are used.
Okay, so what I'll do is, like Nishu has given the email,
Okay.
share the code with this, and any other people who provide their email, we can share the code with them, and so that they can go through the code and understand, and if there is any question they can return back, and plus if there are any errors they can point out. So we'd be happy to have a feedback on that. So Nishu,
Sure.
welcome. You will get all the detail, and hopefully you'll be able to run through it, the recording as well, once we post the recording, which will be after this session. So which is in another, maybe by morning tomorrow, so another 12 hours. And so hopefully we'll be able to have this classification 5.1 under supervised learning be posted there. We have everything up to 4.1, 4.2, so this is a 5.1. What is the 5.2 plan?
5.2 is the continuation of the classification problem itself.
Little bit.
So yeah, it will cover some of the different ways within the. It will be used a different example, like we use the German credit rating for this one. A different data set will be used to explain different topics on that.
Okay, so we'll continue on whatever we had done, further advancing the classification. Is decision table being covered next time, or it will be?
Decision trees will be decision trees will be the part of the
5.2.
for 5.2.
Okay, excellent. So I think Nishu or anybody has any questions, please open yourself, or if you want me, I can stop recording and then you can ask. Okay, I think I'll stop the recording and then let us speak.